Hi everyone, welcome to our today recitation session. Today we will solve questions about connectedness, path connectedness. And lastly, if time permits, we will solve questions related to applications of contracting mapping theorem. Okay, let me share the screen. Problem 1. Let f from x to r real numbers be continuous where x is compact metric space if is the connected component is the connected component of x in x. Prove that f e to the sub x is a closed and bounded interval. Solution. Okay, what can I do? I can first restrict our f to e to the x. Let this clearly this is a continuous function on e to the x. I.e. we have r. As e to the x, ex is a disconnected component is closed, in fact, as connected component containing x, we have ex is compact as closed subset of compact set, closed subset of compact set X. So let me, without the confusion, forget the X, write like this, okay? F attains its maximum and minimum. So as f is continuous and e to the ex is compact, there exists x min, x max in e to the x, so that x min max for all y in this set, the connected component. Call this small n and this is a big N, implies our f is set containing this closed interval. By using the connectedness argument, we will show that in fact they are equal. As ex is connected and and fx min fy x max by IVT for all z in this set. There exists y in here, connected component containing x, such that fy equals to z. Therefore, we conclude that, our set N implies equals to M, again, close bounded interval. Do you have any question? First, we have used some compactness argument, then connectance argument, and we conclude that f is image of f under e to the x, so image of e to the x, so under f is close bounded interval. Problem 2. Let A and B be connected subsets of matrix space, subsets of a matrix space let's say A, prove that if A closure intersection B is non-empty, then this union is connected. Solution. Assume contrary that A union B is disconnected. So, implies there exists CD, let's say matrix space X. They are non-empty and open in X, such that our set A union B contained we don't need to write like that. C union B, A union B intersection C is non-empty, A union B intersection D is, let me write here, A union B intersection D also non-empty, but B intersection G intersection D is empty by definition of connectedness. This implies, in fact, A intersection C intersection D union B intersection C intersection D is empty, then the both must be empty as a union. Okay, call this star. Do you have any question? No. Then, First, A contained in this union, but A intersection C intersection D is empty, implies A intersection C is empty, or B intersection D, so A intersection D is empty, as A is connected. Implies if that guy is empty, A intersection C, we have A contained in D. Or from here, A contained on C. Rule without loss of generality, assume A contained in D. Similarly, second, B contained in C union D, but this set is also empty, implies as B is connected, implies B intersection C empty, or B intersection D empty. One of them must be empty. Implies if this is empty, B contained in D, or B contained in C, respectively. So, by star, A union B contained in C union D, but their A union B intersection C and A union B intersection D is non-empty, implies B is subset of C as a subset of D. Okay, by star, if you check the star, you will see what I mean. Şimdi this set A intersection D, A closure is non-empty. There exists X in here. Implies X in B, but this contains C. C is open. Therefore, there exists epsilon greater than 0 such that the whole ball X epsilon contained in C. But X in A closure implies A intersection. This is not empty, but this is contained in here. But here. A contained in D implies here, let me write, I intersection C is empty. But this is empty. Here it's a contradiction. Therefore, A union B is connected. Part B. If A closure intersection B closure is non-empty, then is it true that A union B is connected? Here, Answer is no. Isn't okay. You may choose A is this open interval, and B this open interval. Then clearly A union B, this is a disjoint union, is disconnected, but A closure and intersection B closure is one point set, which is non-empty. So answer is no. Do you have any question? Problem 3. If x minus boundary of A is connected, prove either interior A or exterior A is empty. Hence, the second part of the question is prove this set is not one. Call this set as A, or is a disconnected subset of plane. Let me pass the other page. Solution. We know we can write for any subset of A, x as interior A union, this is a disjoint, exterior A union boundary A. But this is empty, implies they are both open. So clearly intersection of X with interior A is non-empty if interior A is non-empty. In the beginning we take A must be non-empty, okay, in the beginning question. Our set A must be non-empty. Here, let me write. Maybe here A is non-empty. No need. Sorry. Here, I think. Okay. Now, okay, we conclude easily. A does not need to be non-empty. Okay, maybe empty. It's not so important. Then automatically interior A is empty. So clearly, X intersection interior A. Sorry. They are disjoint open set implies interior A is empty or exterior A is empty. Sorry. Yes. We have a disjoint open sets. Both are open. So, but X is connected, then as X is connected, then interior A or exterior A must be empty. Do you have any question on the second part? Sorry, let me solve the second part. Second part is this. We have a such set. Let me check. Yes, this set. Okay, we can write this as B, where B is what? XY. So x squared, y squared less than or equals to 1. Then interior B is what? Strictly less than 1. Exterior B is, which is non-empty, xy, x squared 1 plus y squared strictly greater than 1, and this is a non-empty. Therefore, by first part, A, which is this set, is disconnected. As an application of the first part of this problem, problem what? I think problem 4. Do you have any question up to here? Prove that a ball in here is convex. Convex means in any point in the ball, we may find a line connecting them, okay? Not a general path, but a line. Convex. Solution. I will do it for a closed ball. Okay, you may try it for open balls. They are same. Proof works similarly. Let B be a closed ball in here. B is this set, xk belongs to here and satisfying this equality. I 1 or 2 less than or equal to epsilon, as it is a closed ball. Now, given any our ball, let's F be a line connecting xy in here. Clearly, this Cartesian product is convex. We have this map. Is take the t sends to 1 minus t times here. Y. Sorry. T times y. Call this z. One need to show. One must show this set contained in our ball, i.e. dza must be D is a D2 here, less than or equal to epsilon. This is equivalent to, for simplicity, we can write like A is a vectors less than or equal to epsilon square, as squared function is 1 to 1. And the whole thing's here positive. Okay. Let me start d squared z a, distance between z a. What is this? This is I 1 to k. So zi minus ai square. So 1 to k. But zeta is what? From here, as you see, this is equivalent to k 1 minus t zi, sorry, xi plus t times yi minus a sub I. Okay, we may write this a sub I as 1 to k 1 minus t xi plus t times yi minus 1 minus t ai minus t ai. So this thing equals to a sub I. Okay, from here, I arrange terms and it becomes 1 to k 1 minus t squared xi minus ai squared. One more step. Let me do one more step. We can write this as I equals to 1 to k 1 minus t squared plus summation I equals to 1 to k again 2 times 1 minus t times plus 1 to k t times y I minus, sorry, let me write in here, plus summation I 1 to k t squared yi minus ai squared. Okay. So let me arrange a little bit. Here, this. Okay. Plus I equals to 1 to k. Here, let me write here t squared. Recall the Cauchy-Schwarz inequality. We have psi e nu e equal to I cosine I square 1 over 2 times I new I square squared. This is what? This is a Cauchy-Schwarz inequality, the specific one of Cauchy. The specific, more general one is Holder inequality. So implies this set I equals to 1 to k, 1 to k, xi minus ai less than yi minus ai times yi minus ai less than, from here, summation I one over 2 times summation I yi minus I sub I 1 over 2, but this is less than epsilon, this is less than or equal to epsilon, so this is less than or equal to epsilon square. Here, let me write the less than or equal, take this, come here. Look at. Okay, this part, this guy, less than or equal to epsilon square, clearly this guy, less than or equal to epsilon square, implies the whole thing is less than or equal to times t 2. If we add this guy, 1 minus 2t plus t square plus 2t minus 2t square plus t square, so times this guy equals to 1, so this part equals to epsilon squared. We get d squared z a, it's a vector, implies one more thing. So F01 contained in our closed ball. Therefore, convex. Similar proof works for the open balls. Okay. Do you have any question? Problem maybe 5. In this button, let me check. So problem 4 has problem 5. Up to here, do you have any question? No. Prove that a metric space is connected if and only if every non-empty proper subset, every non-empty proper subset has a non-empty. Okay, we need to show left-hand side first implies right-hand side, then right-hand side implies left-hand side. Solution. Okay. Now we assume our metric space is connected. So assume X is connected. But assume contrary that, but assume contrary that there exists A, every non-empty proper subset, so non-empty, here it implies properness, such that its boundary is empty. Then we can write X as interior A union exterior A. So boundary is empty. Let's write one more thing. This is empty. Interior A union disjoint union exterior A. So as X is connected, so one of them must be empty. But in fact, we will show that interior, both interior A and exterior A is non-empty, then we will reach a contradiction. Note that, so in fact, as this boundary equals to boundary of the complement, we have so boundary AC is non-empty. Complement of A also has non-empty boundary, empty boundary. Now, as A is non-empty and contained in X, and boundary A is from here we may conclude clearly A complement is non-empty and properly contained in X. As A is non-empty and properly contained in X implies interior A is non-empty, isn't it? If interior A is empty, then A must be empty, so interior A is non-empty. As A complement is non-empty and contained properly in X, and boundary A complement is empty, implies interior X A complement is non-empty, but this is exterior A implies here. If you see both are open and non-empty, implies X is disconnected. This is decided contradiction, okay? Therefore, A is connected. Now, for the second part, the second implication, assume for all A, which is non-empty and properly contained in X, boundary A is non-empty. Now, but assume contrary that X is disconnected. I.e., X can be written like this, say. A union B, they are disjoint, open, and non-empty. Non-empty. So now A is open implies interior A equals to non-empty set A equals to interior A implies interior A. So no need to this part. Okay. As X is disjoint union of these two guys, A and B, then B equals to A complement. This is open, implies, so A complement is B, but B is open, interior B, but interior B equals to interior A complement as B equals to A complement, but this is a interior B, exterior A. So A complement is exterior A, which is B, and they are non-empty. As B is non-empty, we get, X is interior A union exterior. So let me write one more step. A union B, disjoint union, but this is interior A and this is exterior A. But on the other hand, X can be written like this. They are disjoint. Implies boundary A is empty. This is a desired contradiction. Therefore, under that circumstance, X is connected. Do you have any question? Let me solve some more concrete examples. Problem 6. Check whether the following sets are compact connected I will omit the proof of compactness or non-compactness. I will solve this question only for connectedness. Connected the exercise. Let me give it as an exercise and explain your claim. Okay. Our first set is this sine 1 over n in n. Okay, what is this? So this is a 1. Let me draw some picture. Okay, this set here is 1 over 2, 1 over 3, goes like this. this set is excluded. We have at some points here. Clearly, from our picture, we may write as this set ball here choose 2 or 3. Not 2 or 3, be sure. Okay, sign 2 or 3 union ball. So 1. Yes, sorry. This 1 or 2 is enough. One sine 1 minus sine 1 over 2 over 2. Here, note that these are disjoint set and this subset of a subset of this disjoint open intervals. Note that sine 1 over n less than or equal to sine 1 over 2. This is less than 1 over 2. I think this is not correct. Okay. Now, here, take this point. This is call this distance r. Let me consider 1 over 2. If you take the 1 over 2, okay, let me change the sets. Sorry. Call this U union V. I will arrange them. Here, U is xy in r square such that x is less than 3 over 4. Yes. And V is this set. X is greater than 3 over 4. Then clearly these are non-empty sets, disjoint sets. U and V are non-empty and disjoint, and continuous A implies. A is disconnected. Here. This part is U, this part is V. These are our points. A is disconnected. What about this set? X e to the x. Here. This is y equals to e to the x. Our set here. So V is not compact, you may see. Now, in fact, we will show that this B is PET connected, so it's connected. In fact, we will show that B is PET connected or aqueous connected. So write a function. Given any alpha beta in B, we need to find the path connecting alpha and beta. Define clearly implies there exists x, y in our set B such that alpha equals to x e to the x, beta equals to y e to the y. Write our function. So, without loss of generality, assume x is less than y. So, taking t, sending t to the et. As e to the t is increasing function, for all t in xy, for all t in the xy, e to the x less than or equal to e to the t less than or equal to e to the y. Implies t e to the t in B. Therefore, our map, in fact, here is xy to. So inside the B implies B is PET connected, i.e. B is also implies B is connected. Clearly, this function is continuous function. C. This set C is given like this: x, y, z, x squared plus y squared less than 1, less than or equal to 1, intersection x, y, z. This time y squared, z squared less than 4. Now, draw the picture. These are x, y, z coordinate system. Here I only draw the first quadrant. Here it's a 1, 1. It goes like this. And here is from this part is 2, and this going to like sorry. If you, so this portion here, so in the whole part becomes this, the whole part. We have some cylinder here, and from cutting we have this shape. Also inside. So from here, it's a connected. In fact, it's a convex. But how? I will show. Guess that is for all PQ in C and for all T in 0, 1, 1 minus T, P times TQ in here C implies C is convex, implies C is connected. But how? Let me write an algebraically. Let our P, let's say, x1, y1, z1, and our Q, x2, y2, z2. Again, let alpha 1, the first two components. Alpha 2 is the first two components of Q. And beta 1, last two components of P, and beta 2 similarly. Here, one need to show 1 minus T alpha 1 times T alpha 2 after projection. I will write the projection map. Here it's in R square. Beta 1 plus T beta 2. So here this pole. Okay. Now, but I am using this projection maps set to R square, a projection on YZ plane, and PZ here projection on XY plane. From here we get what? C. Z components key by definition of C. C. In fact, it's equal. Implies 1 minus t beta 1 plus t beta 2 in here. And the other page, TZC both 0, 1, which is convex from previous questions. This is a convex set as an open wall implies T from here, so convex. Therefore, C is convex, implies C is connected. D. Let's they will like this, given like this. Define a map F from where to where. This closed wall to real numbers given x, y. Our D is image of F, clearly. Or 0, 1. This is connected, continuous, so whole set is connected. Up to here, do you have any question? So, problem, what? Problem, let me check. Do you have any question?
Yok hocam, 7. problemdeyiz.
Okay, thank you. Problem 7. Show that every open subset A of R real numbers is the countable union, of disjoint open interval. Şimdi solution, we will use the connected components of A. Okay, we may write A like this, x in A, connected component of connected component of x. So as our set A is open and x in A, there exists such that ball x epsilon contained in A. These are connected sets. Any ball is connected. In fact, it's convex, connected, and containing X. But this set is the largest connected set containing X. Implies this ball in fact contains an ear. We do it only for X. Let me do it for any Y. Given any Y in EX, then as a connected component, if you consider the connected component of Y, you will see EY equals to EX. Similarly, for this Y, there exist by similar arguments delta, let me say epsilon X, there exists epsilon Y greater than 0 such that ball Y epsilon Y contained in here. From here, we conclude what? Implies EX is open. Open, also it's a connected, also it is connected, therefore EX is open interval. Connectedness implies the EX in R open interval in real numbers. So we'll how conclude EX is connected implies EX is interval in R, but EX is open connected implies EX is open interval. R. Okay, so in fact, but as Q closure, the rational numbers is R, we conclude that any open interval contains a rational number from here. Therefore, there exists Q in Q for all X, so in Q such that EX equals to EQ. So we can write AS union is a disjoint for some Q in Q, EQ. This is a countable union of open intervals as index set is subset of Q. Subset of Q, countable. Okay, therefore, now every open set A of real numbers is the countable union of disjoint open intervals. Okay? Any connected components does not intersect with other connected components. If they intersect, they are same. Problem 8. Problem 8. 4 points x and y of a metric space X. We write X related to Y if there is an arc joining or path joining X to Y. Proof this is an equivalence relation. We will show that it's reflexive, symmetric, and transitive. First, it is reflexive. Let gamma 0, 1, 2, or AB2, let's say AB2, to X, sending T to X, constant path. So clearly this is a continuous, and gamma A is X equals to gamma B, implies X related to X. Let me write here. Given any X and X fixed constant path, so it is a reflexive. So what about the symmetricity? For all x, y in X, if X is related to Y, I mean we have an arc joining X and Y, then we have continuous path, continuous A to B to X is closed interval to X, such that gamma A is X and gamma B is Y. Consider another path, again AB to X, given as Y gamma T equals to Y tilde T, gamma tilde T is gamma A plus B minus T. Clearly gamma is continuous, so gamma tilde as composition of continuous functions. Okay, from here, and gamma tilde A is what? A plus B minus A, gamma B, which is Y, and gamma tilde B is gamma A plus B minus B, which is gamma A, and it is X, implies Y related to X. So our relation is symmetric. What about the transitivity? For all x, y, z in X, if X related to Y and Y related to Z, we need to show that X related to Z. Then we have two paths, gamma AB to X and new AB to X. Gamma is arc joining X and Y, and nu is arc joining Y and Z. I.e., gamma A is X and gamma B is Y, nu A is Y and nu B is Z. Then define etmişiz. I use this symbol rho. Gamma 2t minus a if t is here. A plus b over 2, and nu 2t minus b if t in here. Here, so gamma t, gamma ab to x. Gamma is continuous as both components are continuous and agree on t equals to a plus b over 2. And gamma a is what? Rho a, not gamma, rho a is gamma 2a minus a, which is gamma a, is x. Gamma b is what? Oh, sorry, rho b is nu 2b minus b is nu b. This is z, implies x related to z. Hence, our relation is equivalence relation. Therefore, so she is equivalence relation. Problem. Sorry. Problem 8. Now we come to problem 9. Do you have any question? Now we come to applications of contracting mapping theorem. Where is that question? Okay. Let theta 0, theta 1 be mappings of a complete metric space, metric space X into itself, i.e. theta is x to x, such that for some M1 we have this inequality. What is it? It means all theta i's are contracting mapping for all x, y in X. It means they are unique fixed points. Suppose limit theta and x is theta 0 x for all x in X. Let these points x0, x1 goes like this, be the unique fixed points of theta 0, theta 1, respectively. Now, prove limit xn is x0. Okay, so solution. Observe that d x sub n, x sub 0, as they are fixed points of theta n and theta 0, theta n xn, theta n x0, sorry, this is theta 0 x0 as a fixed points, but this is less than or equal to, by triangular inequality, plus okay, but the first guy, a d xn x0, by property given in the question. So this thing is less than or equal to a implies, if you arrange the terms, 1 minus a distance xn to x0 less than or equal to this guy. This is strictly greater than 0. Let's sorry. Strictly a positive number. Okay. Now, as limit theta n x0, this is true for 4 of x. Is a theta. Given epsilon greater than 0, there exists n0 in natural numbers such that for all n greater than n sub 0, we have d n x0 minus, sorry, not minus, x0 less than or equal to 1 minus a, not less than, less than. We find n0 as this is a positive number. Implies for given n0, the xn x0, or let me check. Oh, okay. Less than 1 over 1 minus a, the theta n x0, theta 0 x0, hop, hop. This is less than minus a. Okay, implies limit xn is x0. Do you have any question? problem 10. Any question? This is the last questions in this recitation, which I will solve. So by considering the function, which function? This function given like this, minus log prove that logarithm 1 plus b of 1 plus a, b minus a for 0 less than or equal to a less than or equal to b. Now let the second part of the question. 1. Prove that there is a unique continuous non-negative real valued function f on 0, 1 such that f as 1 plus logarithm 1 plus rho ft dt. Define theta from here to here. Clearly, this is a complete metric space with respect to submetric. Takes f and send it 1 plus logarithm absolute dt. We will show that theta has unique fixed point. Unique fixed point. Okay. Okay. Now let me solve the first part. If a equals to b, then clearly logarithm 1 plus b over 1 plus a is logarithm 1, which is 0, 0, which is b minus a. Assume a is less than b. Okay. So our function g, t minus a minus logarithm 1 plus t over 1 plus a. Then g is continuous on AB and differentiable on AB. So by mean value theorem, there exists alpha in AB such that G prime alpha is GB minus GA B minus A. This is B minus A minus logarithm 1 plus a over b minus a. So g prime alpha is clearly implies g prime alpha 1 minus what's the derivative of logarithm? So 1 over 1 plus a, sorry, is alpha. This is 1 minus logarithm 1 plus b over b minus a. Sorry. Logarithm 1 plus b 1 plus a over b minus a. Okay, these two are cancelled. We have implies logarithm 1 plus b over 1 plus a over b minus a. But alpha is something positive. Implies this is less than 1. Therefore, we have logarithm b minus a. Okay, in fact, we have more. Look at this. In fact, let me write. In fact, we have more. I logarithm 1 plus b over 1 plus a, the absolute less than or equal to absolute b minus a. So b greater than a, we are none. Assume b less than or a implies these things equals to minus logarithm 1 plus b over 1 plus a, as that thing is negative. So clearly this is equals to logarithm 1 plus a over 1 plus b, but here a is greater than b, implies this is less than a minus b, but this is absolute value of b minus a as b is less than a. Hence we get absolute logarithm 1 plus b over 1 plus a is less than or equal to b minus a absolute for okay. Now our claim in the beginning, our theta function, theta has a unique fixed point. One need to show our theta is contracting mapping. So given any let's say alpha beta in here, d sub alpha beta equals to, so theta alpha theta beta equals to supremum theta alpha t minus theta beta t t 0, 1. Okay, this is equal to supremum. Oof. Logarithm 1 plus rho times integral 0 to s alpha t absolute value dt minus logarithm 1 artı rho 0 to s beta t absolute dt here s in here s in not s t in 0, 1. Okay, o'clock. But from the properties of logarithm, we have supremum, absolute logarithm 1 plus 0s 1 plus this thing beta t dt t in 0, 1. Okay, but we know this is less than or equal to, if you call this is a, okay, this thing a and this thing b, by the beginning of the by the first part of this question, we have rho of implies this is less than or equal to supremum, but this is also less than or equal to that guy. Also, one more thing. As in here. So we have supremum, this thing. Okay, take outside, it's a positive number. Alpha t minus beta t in. So this is t sub alpha beta. Then we get t sub theta alpha and theta beta equal to this number case 1. If the rho is 0, then our inequality, so then clearly take f is 1, so ft is 1, constant function. I1 equals to 1 plus logarithm 1 plus this thing. But this is, this cancels. Okay, let me write 0s absolute 1 pt. This is 0 implies this is 1. Okay, case 2. So ft1 equals to 1 is required unique function. If this thing is less than, sorry, case 2, if this thing here, strictly here, then theta is contractive mapping as d sub theta alpha, theta beta, alpha beta, for all alpha beta in here. There exists unique fixed point of this theta, let's say f in here. F equals to theta f is equal to 1 plus logarithm 1 plus 0 less absolute f dt. But note that here f is a non-negative function, implies this guy 0. So this thing is less than 1, greater than 1, so the whole thing is greater than or equal to 0. So this is greater than or equal to 0. Whole thing is greater than or equal to 1, implies greater than 0. Therefore, f is positive, i.e. absolute f is f. We get hence, in the question it says, hence this function is unique continuous function, is unique continuous real valued function. Function on 0, 1. Okay, do you have any question? This is end of our recitation. Now I'm stopping the recording. Yes.